Hello guys, welcome to this video. And in today's video, we're going to be essentially speaking about hemoglobin. We're going to be speaking about the the Bohr effect and how the dissociation curve kind of functions. So I have over here I want to start off first of all hemoglobin. And now I'm going to be asking you guys a quick question. How many subunits do you think the hemoglobin is kind of made out of? So if you're saying four, that's completely correct. Okay, there's two alpha units, four polypeptide subunits. Okay, the normal adult hemoglobin is made of four polypeptide subunits. Two are alpha, two are beta, as shown in this photo. One, two, three, four. All right, and that each bind one molecule. So we can see each has a heme part, heme. Of course, the hemoglobin is broken down into heme and globin. So heme, it binds oxygen, and globin is kind of the protein. Hemoglobin is an allosteric protein that exhibits a positive cooperativity with O2 is such that oxygen hemoglobin has a high affinity for O2. So what does this kind of mean allosteric? Allosteric means positive cooperation. Okay, what do I mean by that? Okay, so imagine hemoglobin is like for example the present. Okay, hemoglobin is a present. It kind of binds with oxygen. Okay, now once it binds, it kind of changes its shape to have positive cooperativity. So it can bind more oxygen. So it will now the hemoglobin will kind of change its shape and bind to more oxygen, and it will change its shape and bind to more oxygen. Okay, so we can see that the allosteric feature of hemoglobin is I can change the shape, allow it to bind to more oxygen, more oxygen, more oxygen. Okay, and that's really good because when you're in a hypoxia situation, you want hemoglobin to bind more oxygen. And for example, in the next statement over here, deoxygen hemoglobin has a low affinity for O2, but when you're releasing unloading of O2. And now I'm gonna be asking you a question. If you're gonna be in a scenario you're gonna be have to give oxygen to your tissues, do you want your hemoglobin to let go of oxygen, or do you want your hemoglobin to stay tight to oxygen? So let go or stay tight. Let me know. Yes, you want it to be let go in a state where there is deoxygenated hemoglobin. You want oxygen to let go because you want it to go to the tissue. Now let's come over here. The protein component of hemoglobin acts as a buffer for H plus ions. What does this mean? Of course, the hemoglobin is going to be the heme part, and we have the globin part. Heme is kind of where the iron is. It binds the oxygen, okay? And we have four of these. We also have the globin part. Now, I'm going to ask you, do you know what kind of globin is? What is your kind of concept of globin? A globin is essentially a protein. It can bind a few stuff. It can bind your hydrogen or it can bind your CO2. And in this scenario, we are going to be speaking as it acts as a buffer for H plus and CO2. What do I mean by this? Now, let's just say the protein component, it has a component of hemoglobin acts as a buffer H plus and CO2. Okay, so essentially CO2, it would enter kind of a cell. It would then, once it enter CO2 in cells, it combines with H2O, and it would then become hydrogen ions and bicarb. So that would be the two main things that it becomes over here. So now I'm going to be asking you guys a question if you're watching this clip. That let's just say you have a lot of CO2 entering the cell, a lot of CO2. Where would kind of the equilibrium shift? Would it shift right or kind of shift left? Yes, to balance out, it will shift right. So we're going to be having increased amount of H plus. So that's kind of how it acts as a buffer. Now, myoglobin is composed of a single polypeptide chain composed of one heme moiety. Now, I want you to, when I speak of myoglobin, I wanted to compare it to hemoglobin. And hemoglobin is shown over here. Hemoglobin over here has how many polypeptide chains? Does it have two? Does it have three? Does it have four? How many? Four. And how much does myoglobin have? It has one. Okay. So myoglobin is enclosed as a single polypeptide chain with one heme moiety, a high affinity for oxygen than hemoglobin. Now, of course, if it has one hemoglobin chain, one polypeptide chain, of course, that one chain is going to have higher affinity for oxygen compared to the four over here, which are going to be kind of averaged out. essential for full oxygenation of aerobically active muscle. Now, this is important. Aerobically active muscle. I'm going to draw a picture over here. Myoglobin, as we know the name, is myo, which is muscles, and globin means a protein. Now, myoglobin is going to be very important for our muscles, okay? So it's going to be there for our muscles because our muscles are going to be exercising. We're going to be in the gym, we're going to be cycling, we're going to be running, we're going to be playing football, soccer. We need our myoglobin to be going to our muscles. So you can just imagine myoglobin like a stronger version of hemoglobin. So myoglobin is going to be a stronger version, I would not say stronger, I would say higher affinity, increased affinity for O2 if I compare it to his brother, hemoglobin. Now let's come into the next page over here. And we're going to be speaking about O2 content of the blood. For O2 content of the blood, we're going to have to refer to this formula. O2 content depends on two key things. O2 bound to hemoglobin and O2 solubilized in the plasma. O2 bound hemoglobin is 1.34, and why 1.34? It's very important, times the hemoglobin concentrate. 1.34 is going to be here because normally 1 gram of hemoglobin can bind to 1.34 ml of O2. So your hemoglobin is directly proportional to 1.34, as that's the constant that it can bind to. 1 gram can bind to 1.34 hemoglobin. Next is saturation. I'm going to ask you guys, what does saturation mean? Does saturation mean kind of like sticking together, or does saturation mean kind of molecules staying apart? I'm going to ask you guys watching this clip. So if you're saying saturation means two molecules sticking together, that's completely correct. That's what saturation means. And 0.003 times partial pressure of O2. So 0.03 is the solubility constant of O2 times the partial pressure, the kind of the pressure of O2 in the blood. So yeah, SaO2, as we spoke about, percentage of saturation of arterial blood with O2. So the amount is stickiness. 0.003 is going to be the solubility constant of O2, partial pressure of O2 in arterial blood. So we can see normally 1 gram of hemoglobin can bind to 1.34 milliliters of O2. Normal hemoglobin in blood is 15 gram per deciliter. So normally, if you have 1 gram of hemoglobin, okay, it would then bind to 1.34 milliliters of O2. And then we can see normal hemoglobin in the blood, how much we have. And normally in our blood, we have 15 grams per milliliter. So if we have a blood over here, we have a total, we can, in per deciliter of blood, we will have 15 grams of hemoglobin. And of course, one gram, this is 15 gram, and if you were to take 1 gram, it would be able to bind 1.34 milliliters of O2. O2 binding carrying capacity is 20 ml of O2 per deciliter of blood. So the carrying capacity is going to be 20 ml of O2 per deciliter of blood. When there's a decrease in hemoglobin, there's a decrease in O2 content of arterial blood. There's no change in O2 saturation or partial pressure of O2. That's an important concept. When we get a decrease of our hemoglobin, now I'm going to ask you guys watching the clip, when do we get a decrease of hemoglobin? When do we think? So you're thinking about any bleeding, that's completely correct. Any sort of anemia, that's completely correct. Any sort of maybe damage to the bone marrow, which kind of produces your red blood cells, is going to be completely correct as well. Any of these scenarios would be a decrease. There's definitely going to be a decrease on O2 in the arterial blood. I want you guys to have this concept. This is the blood vessel, and the blood is like the river. It's literally like a river over here. And we have boats in the river. We have many, many boats, and those are RBCs. Now imagine there is going to be some sort of like leakage in this river. Okay, there's going to be some leakage in this river. That's going to be leading to less amount of RBCs, less amount of hemoglobin. Or there's some production defect. We're going to have red amount of bloats and red amount of hemoglobin. But saturation essentially means your stickiness. Saturation means your stickiness. And your PaA2 means your partial pressure. O2 delivery to tissues, cardiac output times O2 content of blood. So that cardiac output times O2 content of blood. So we can see what is going to be over here. Let's see carbon monoxide. Carbon monoxide is going to be a problem in what? It's going to be a problem in content, saturation, partial pressure, or total content. It's going to be a problem with saturation. The key issue here is your saturation. CO2 competes with O2. CO2, the RBC loves CO2. It loves CO2. And we can see everything else is normal, and that would lead to a decrease in total O2 content. Anemia, okay, anemia again, we're gonna have decreased hemoglobin over here. Everything else is normal, and that leads to a decreased content. Let's look at the opposite, polycythemia. We're gonna have it increase, and that's gonna increase amount of O2 content. Methemoglobin, it's gonna have again, it's same as carbon dioxide, a decreased amount of your saturation, your stickiness, and that's gonna be leading to decreased O2 content. Cyanotoxin, everything is fine. What's the problem with cyanotoxin? For cyanide toxin, which part of the RBC? I mean, not necessarily the RBC, but essentially cyanide poisoning in other tissues, it affects the mitochondrium. So if you kind of draw a diagram of the mitochondrium, and the mitochondria is going to have this thing called the electron transport chain, ETC over here. So it involves one of the enzymes, the cytochrome C oxidase in the electron transport chain. And when it kind of blocks that cyanide, we're not going to be able to kind of use your oxygen. We're not be able to make ATP. So cyanide toxicity is a problem with using oxygen. You have everything is fine. Your hemoglobin, your saturation, your partial pressure, total content. But the ability for you to utilize it, it's going to be a problem. So everything is fine. Just you cannot use oxygen. So you are going to be in a state of hypoxia, and you're going to be shifting towards anaerobic glycolysis metabolism. Oxyhemoglobin dissociation curve, so the ODC. Okay, a shift in oxygen hemoglobin dissociation curve reflects a local tissue oxygen needs. Can be helpful, meets metabolic needs, or harmful toxicity and pathological conditions. So I want you guys to know two things: right shift and left shift. Right shift and left shift. Before I dive into this, I want you guys to tell me, do you know maybe what's the cause of right, what's the cause of left? So let's build a concept. Right shift, which is shown over here, and left shift. Right shift means less stickiness. You're not sticking with the RBC or hemoglobin that much. And left shift over here means increased amount of stickiness. You're sticking on. When do you think we're going to have less stickiness? Less stickiness is going to be in a scenario where your body does not need oxygen. It's letting go of oxygen. And increased amount of stickiness is a scenario where your body kind of needs your body does not need oxygen. So in a well oxygen area, like maybe your tissues are well oxygenated. So you're gonna have right shift or left shift. You're gonna have three key components. There's three key components. Okay, one, two, and three. Okay, let's come over here with the one. Decreased hemoglobin affinity for O2, increased O2 loading at tissue, physiology caused by increased O2 needs. First one is going to be exercise. They mentioned it over here. Exercise. Exercise is a state of increased amount of temperature, increased amount of fever. We're metabolizing more, so increased amount of exercise. Now, why exercise? Okay, because when you have an increased amount of temperature, now I'm going to ask you the temperature. What's going to be kind of the bonds between hemoglobin and oxygen? It's going to become quite weak, and that's going to lead to oxygen kind of being dissociated. Okay, and that's going to be release of oxygen. Okay, it's going to go to our tissues or muscles which need oxygen. The second thing is going to be hypoxia. Okay, hypoxia, right? It's going to be hypoxia. It's going to lead to increased amount of glycolysis. An increased amount of glycolysis, we get a thing called 2,3-biphosphoglycerate and at the cellular level. And that essentially leads to more amount of kicking off of your essentially your leads to less affinity of O2 and hemoglobin, and more O2 goes to the blood. Then we can see we're here caused by increased H plus, so that's going to be increased amount of H plus. So that's going to be any sort of decreased pH, where we're having a lot of CO2, got tissue metabolism, and the Bohr effect. So we're having a lot of anaerobic metabolism. We're not producing a lot of oxygen. So therefore, there's going to be a lot of letting go of your O2. That's going to be the Bohr effect. And the left shift in the oxygen dissociation the oxyhemoglobin dissociation curve is essentially the opposite. We spoke about increased temperature, decreased temperature. We spoke about increased 2,3-biphosphoglycerate, decreased 2,3-biphosphoglycerate. We spoke about increased H plus, but we're going to speak about decreased H plus. So decreased O2 loading physiologically with decreased O2 needs, decreased temperature, and in pregnancy, fetal hemoglobin has higher O2 affinity and the adult hemoglobin, and increased O2 binding due to decreased affinity of 2,3-biphosphoglycerate, left shift O2 across the placenta. Pathology caused with increased amount of CO, increased amount of hemoglobin, genetic mutations, and decrease. Oops, sorry. To phosphorylation, left is going to be lower. Oxyhemoglobin dissociation curve is a sigmoid shape, And due to there's going to be positive cooperation of the tetrameric hemoglobin, four molecules are highly affinitive, more subsequent O2 molecule bonding. Myoglobin is monomeric and has no positive cooperation, therefore would lack the sigmoid curve. Coming into here, the questions. How many molecules of O2 does one hemoglobin bind? So 1, 2, 3, 4. Remember, it's a tetramer, so it's going to be 4 molecules. Which of the following is true about myoglobin? It gets compared a 4 polypeptide chain. That's wrong. It's compared it's a 1. It has a low affinity for oxygen hemoglobin. No, in fact, has more. It has only one binding site. It is essential for full oxygenation for aerobically active muscles. That is completely correct. And then we can see binds to O2 molecule. That's wrong. When conditions causes a decrease in total O2 content, but no change in SaO2 and PaO2. So that's going to be in the scenarios such as, let's look at carbon monoxide. It causes a decrease, but carbon monoxide is a problem with saturation, so therefore this is wrong. Anemia is going to be causing a uh, could be the potentially correct answer. A decrease in total O2 is going to be definitely not hypocemia, that would increase it. And hypoxia, that looks like an interesting answer. So it's between B and D. So over here, it would essentially lead, I believe it'd be D, as anemia would lead to a decreased amount of partial pressure. What is the normal amount of hemoglobin in blood? So that's going to be 10, 15, or 20. So that's going to be 20 grams per deciliter. And we have a 25-year-old male running a marathon, and his exercising skeletal muscle tissue. Local conditions cause oxyhemoglobin curve to shift to the right. And this is me the which set of physiological changes is responsible for the shift. So increased amount of pH, decreased temperature, decreased 2T bisphosphoglycerate. Um, mm, so we're moving to the right, where essentially if someone's running, we would have increased 2T bisphosphoglycerate. So this is wrong. Decreased CO2, that is also wrong, as when we're exercising, we're going to be having increased amount of CO2. Increased amount of H plus and CO2, increased temperature looks completely correct. Increased pH will be incorrect, as we're going to be having a decrease in H plus. And I believe this is going to be, yes, so we have the similar question over here. We have, if someone is going to be exercising and is shifting to the right, what we expect decrease pH would be, increased pH would be wrong. It would be increased pH, increase which, and increase in everything. And this would also be wrong, as we're having a decrease in pH. So guys, that was a quick video about hemoglobin and O2 kind of content. So we see in O2, it has 4 binding sites. If we have more oxygen, it binds more allosterically, positive cooperation. Decrease O2, less binding. We in O2 content, we look at saturation, look at partial pressure, and that kind of helps us to determine this. Well, oxide hemoglobin curve, 3 main physiological causes is increased H plus, increased temperature, and an increased amount of plus temperature, and increased amount of 2,3 bisphosphoglycerate. And the opposite is true when moving left. So hopefully you found this video useful. Thank you for watching. I hope to see you guys next time.